Good morning, all my honors students. Welcome to your second podcast of this chapter. We are going to go a little bit further than what we did in class today. And by the way, you guys did an outstanding job in the questions that you're asking and hanging in there. Hopefully those will start making a little more sense. So we talked about Rutherford's model, where Rutherford just figured out that he had a nucleus. Well, if you think about that nucleus being positively charged, and then you just have the electrons around the outside, why aren't those electrons just sitting, glopping right on the nucleus, when in actuality there's a lot of space between the nucleus and the first energy level? So then that's when Niels Bohr came along and proposed that electrons orbit around the nucleus like planets. So down in this picture down here, he believed that the electrons orbited in certain rigid patterns. And what we talked about today, that they really aren't as rigid as once thought. But still, we're going to call them energy levels. And we could talk about electrons going from one level to another, that they have to gain and lose energy, and that's how they emit light. And keep in mind that the further the distance we are away, the amount of energy that's going to be involved in our system. So we are fairly convinced that Bohr's model had to be modified, and the Heisenberg uncertainty principle came along, and it talked about that it's impossible to measure both the position and the momentum of a particle in a given point of time. We talked about that if all of us little rock stars were actually electrons in our classroom, that at whatever hour you're in my class, we could probably figure out most of the time where you are, that you're in A309, but we don't really know your position or your momentum at that given point in time, because it might be different. We might be back in lab, you might be sharpening your pencil, Miss Benson might be telling Jacob Frender to be quiet. I told you, Jacob, I was going to mention your name. Whatever it is, but we can essentially know where you are in my room, but we can't really say specifically your position. And so we know that the Bohr model needed more work. And so that's what we are going to be trying to take a look at with our models that I was showing you today. So the wave mechanical model was first taken a look and studied by Erwin Schrödinger. And what he found is he used mathematical equations to describe the location and the energy of electrons in an atom. So he figured out the electron probability cloud. And remember today I was really trying to get you guys to understand that it was just a region where the electrons travel. It is not a fixed hard sphere like my models were. So it's probability of finding an electron 90% of the time. So if we take a look at this dot density over here, we can see that this is going to be our nucleus right in the center. And then if you remember, for hydrogen and helium, we had those two electrons. And those two electrons, at whatever given point in time, they are traveling around in this first energy level. If you recall, this will be called the 1s energy level, because it's the smallest one, it's the one closest to the nucleus. And we talked about that if you have more than two electrons, well then we need to go into another energy level. And you can again see that they are just traveling about here at some point in time, at any moment, but they are moving around in this region. It doesn't mean that it is a hard fixed position. And so that would be called the second energy level, or in this case you could say that n is equal to 1 and n is equal to 2. Well, what is n? N is the principal energy level. And so describe where the electrons can probably be found. We're going to talk about our principal energy level, or simply energy levels. So it describes the distance from the nucleus where the probability of finding an electron. So n equals 1, n equals 2, n equals 3, and these are going to be our energy levels. You can see that if I have n equals 1, that would be the 1s region, and this has the lowest energy. It is closest to the nucleus. It doesn't take a ton of energy to hold in those electrons. Now, we can have an electron, if it gains enough energy, go all the way out to infinity. So that should make sense to you that it's going to take the highest amount of energy available in a system to kick that electron out and come back home and emit light. And so again, if you're taking a look at this real simple, we have our nucleus, we have our energy levels, the first one closest, then we have the second energy level, and we keep going out and out and out. And actually they do keep getting closer and closer and closer to each other as we keep going further and further and further out. Now keep in mind that as we take a look at this, that if this is energy level 1 right here, and this is energy level 2 going out to the second energy level, and then energy level 3, that all of these have different amounts of energy. So this one out here would have my greatest amount of energy needed to hold those electrons in. You have to keep in mind that I have these positive protons way back here trying to attract these electrons and keep it close. So the higher the N value, the higher the energy and farther from the nucleus. Okay, moving right along. We can say now we have our energy levels. Well, within these levels, there's called sublevels. So we have the distance from the energy level. Now we want the shape from the sublevel. So if I'm in the first energy level, second energy, third energy level, whichever one we are, we want to know what the shape is within those energy levels. So the types are S, P, D, and F. There is G, there is much more. We are going to stick with the first 4 as you drew on your periodic charts today. So a little bit of review, if you recall that we have our S orbitals, and remember that they can hold 2 electrons, very low energy, cannot hold in a lot of electrons. They're spherical shape. Again, this is a probability 90% of the time of finding an electron. Well, we know that we have more than just 2 electrons on our periodic chart. And so from there, I showed you today in class that we went to p orbitals. And remember that p orbitals can hold up to 6 electrons, and they are ellipsoidal shape, a dumbbell shape, and we can envision an electron here, in all these different regions. And then when they all come together, remember this is a region where the electrons are traveling. We still have the 2s, we still have the 1s, and we still have our nucleus in the center. So they all have different orientations, x, y, and z, and it depends what element we are talking about as to how many electrons there are available. Now, these p orbitals have nodes. In the s orbital, you don't have any because the whole region is enclosed. So this, for the p orbital, is a region near the nucleus where the probability of finding an electron is low. You can see all these regions along here that finding an electron in that sublevel is going to be very difficult. All right, then if we go to the next sublevel, which is going to be the d orbitals. The d orbitals are mainly in the transition metals, and you can see that right here. And they can hold up to 10 electrons. And they are a cloverleaf shape. And again, you can see all the different orientations that those electrons can hold. So I'd have 2 here, and 2 here, and 2 here, all the way up until I got my 10 electrons. And you can see if I put them all together, this is what they're going to look like. If I could slice this open, keep in mind, I have my nucleus in the middle, I have my 1s, I have my 2s, and I don't even get to the 3 sublevel, or the 3ds, until I get to my 4th energy level. So here's my 3s, so I'm way out here at my 4s before I'm even getting into the d sublevel. So you have to keep in mind that I have all these electrons flying around underneath in these specific regions. So we're trying to build out from our model so that you guys can understand what's going on. Okay, then the next one, we have our f orbitals, and again, they can hold 14 electrons, and those are those rare earth metals down at the very bottom. They are complicated, they are difficult to visualize. For the most part, we never classify them as having any shape, because all they're doing is they really are filling in the shape outside of here. So if you can think about this D-shaped thing, then we have these F orbitals out here, and they follow some sort of pattern, but it's really just not a shape that we can identify with. And I know they have drawn some shapes here, but again, it's just regions filling in outside of that D orbital. Okay, so one little summary here that I'm going to get you guys started and see if you can fill this in then. So principal energy level, remember, is N equals 1. The number of sublevels that are there is only 1, and the sublevel that's there is an S. If I go to my second energy level, again, I have S, and before I can move any further, I have my P sublevel. So go ahead and see if you can fill those in. In class, we're going to start talking about orbitals. An orbital is a place that 2 electrons can go. So here in my first energy level, I have an S, and I can hold 2 electrons. An orbital can hold 2 electrons. And then I have my 2s if I'm in the second energy level. Again, s's can only hold 2 electrons, so it's 1 orbital. And they travel in pairs. That's why there's only 1 orbital. And then if you go to the p's, you recall it can hold a total of 6 electrons. So 6 divided by 2 would be 3 orbitals. And each orbital can hold 2 electrons. And so now I have room for 6. So see if you can figure out n equals 3 and n equals 4. If not, we will take a look at that tomorrow. And we'll finish up the rest of this at that time. So I hope this gives a little more idea of what I'm doing. I know I'm repeating a lot of things I did in class, but this is all brand new material, and I think it's worth repeating. You guys have a wonderful night, and I will see you in the morning.